I ran a quantum computer against a classical algorithm. The quantum computer won. Kind of. Here's what actually happened. So there's this concept called reservoir computing. You feed chaotic time series data into a fixed complex system and only train a simple linear layer on top. The system itself never gets trained, it just transforms the data into something learnable. Classically, you'd use a big random neural network for this. I replaced that with a quantum circuit. 6 qubits, random rotation gates, entanglement. Feed in the data, measure the output probabilities, train a linear layer on those, that's it. I tested it against a classical echo state network on the Lorenz system, basically predicting chaotic math equations one step ahead. The classical network got an MEC or mean squared error of 0.000881, really clean. Then I ran the quantum version at 5 noise levels, 0% up to 20% depolarizing noise to see if there is a sweet spot where noise actually helps. Long story short, there wasn't. Noise just made things worse every single time. At 20%, the circuit is basically outputting a flat line. I ran it across 3 different random circuit seeds to make sure, but the results were more or less the same. Then I ran it on real IBM quantum hardware, and this is where it got strange. The hardware MSE came in at 0.000288, better than every simulated noise level, better than the classical algorithm. Real quantum hardware, noisy and imperfect, outperformed the noiseless simulation and the classical baseline. I still don't have a clean explanation for that. So I thought maybe quantum just does better in noisy real-world situations. To test that, I ran both models on real monthly sunspot data, 300 months of actual solar activity observations, messy, irregular, real-world data. And here, the classical ESN won, 0.013408 versus 0.016486. Not a huge gap, but quantum didn't pull ahead as I expected it to. So putting it together, quantum lost on simulated data, surprisingly won on real hardware for the clean mathematical Lorenz system, and lost again on messy real-world sunspot data. My original hypothesis was that quantum would shine in noisy real-world settings. That didn't pan out. Instead, the quantum advantage showed up in the more structured deterministic task and only on real hardware, which honestly raises more questions than it answers. One thing I wanted to make sure came out of this project was something people could actually use. So I packaged the core experiment into a standalone tool called the QRC Noise Characterizer. The idea is simple. You point it at your own IBM quantum backend, it builds a simulated noise curve automatically on your local machine, then runs your real hardware and estimates your backend's effective noise level as a concrete percentage by interpolating where the hardware result falls on that curve. So instead of just knowing your gate error rates or T1, T2 times, which are hard to reason about intuitively, you get a single number. This backend behaves like a system with roughly X% depolarizing noise. You can use it to compare backends, track how a backend's noise changes over time, or just get a feel for what you're working with before running something more serious. The full code for this is on GitHub and the full write-up is on Medium. I've put the links in the description for you to check them out.